Hello, and welcome to a series of videos that are meant to get you ready for your final exam in this course. So let's take a look at what we have here. All right, the data below refers to the size of plants in a recent agricultural study. Sketch a histogram to summarize the data above. What are you using as your bin width? Once you have the histogram, describe the distribution, which includes the shape, the spread, and the center. All right. So, histograms, all right? It's basically as if you're taking your data and putting it into little baskets, all right? And then you're counting how much data falls in each basket. Now, they can either be relative histograms, where we're working with percentages, or they can be frequency histograms, where we're working with counts. Either way, the fundamental idea is the same. You're either adding up the counts or you're adding up the percentages. So in this case, we have lengths ranging from 1 to 15, and those are each associated with different percents. So the lengths can make up our baskets, all right? We might have one basket that includes lengths 1 through 3, another one that includes 4 through 6, another one that's 7 through 9, 10 through 12, 13 through 15. All right, your basket should always be of equal width. So I've got 5 baskets, all of which contain 3 different values. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I need to go through and I need to add up what those entail. So altogether, 3.6, 14.8, 18.7 is 37.1% of the observations are length 1, 2, and 3. All right, 16, 12.5, 8.2, 36.7 of my observations are length 4, 5, and 6. And then we just keep going from there. All right, this one's going to be 18.4. This one's going to be 6.6. And this one's going to be 1.2. All right, but I'm kind of condensing these 3 individual options into a single basket and then summing up those values. Condensing these 3 options into a single basket, summing up the values, and so on and so forth. So when I'm making my actual histogram, when I'm sketching it, all right, I might say, what do we want to put on the bottom here? Lengths, right? Because these are the different lengths that I'm measuring. And then on the left-hand side, it's either going to be percentages or counts, all right? If it's a frequency histogram, it's going to be counts. If it's a relative frequency histogram, it's going to be percentage or percents, all right? Now, the bars, I could do this a couple of ways. I could label them as like 1 to 3, 4 to 6, 7 to 9, 10 to 12, 13 to 15. Or I could use inequalities. So I could say, all right, this one starts at 1 and it goes to less than 4, which is another way of saying 1, 2, and 3. This one starts at 4 and goes to less than 7. This one starts at 7 and goes to less than 10. This one starts at 10 and goes to less than 13. And this one starts at 13 and goes to less than 16. All right, so that's one way I can do it. The other way is I could have just underneath each one labeled it like, oh, this one is 1 to 3. This one is 4 to 6. This one is 7 to 9. This one's 10 to 12. And this one's 13 to 15. All right. And then I'm just making the bars that go up to the height that I've already calculated up here. So again, as it's been all year long, I'm not going to take off points if things are slightly off. I'm just looking for a general picture of sort of what's happening here. So I'm going to call this, 37.1%. I'm going to make 36.7% just a tiny bit lower, but almost the same. I'm going to make this 18.4, about half the size of those. And then 6.66 will be down here. And then we'll have a 1.2, which is all the way down there. All right, so that gives me kind of a rough idea of what we're looking for. Now, as far as the other information that we asked for, our bin width was 3. All right, we put 3 different values inside of each basket and then sum those baskets. The shape, all right, our distribution tails off to the right, so we would say that this is skewed right. When a distribution is skewed, all right, the measure of center we should be using is the median, not the mean. All right. And the median is the 50% mark. All right. It's halfway through the data. So if this is 37.1%, this brings us up to 47.53%. So this is going to be where we hit 50%. All right. That's 50% of the way through the data. So our median is going to be 4. All right. And then if we're measuring the spread, we can look at things like the IQR and we can look at things like the range. So the range is going to be the min minus the max minus the min. Now, it's not these percentages. That's just telling you how much of each observation you have. Your observations go from 15 to 1, which means you have a range of 14. All right. If we were doing the IQR, that's Q3 minus Q1. Now, again, Q1 is the 25% mark in your data. So, again, 25% is going to fall in this area right here. 3.6 plus 14.8 is like 18.4. And then this is going to get us to 25%. And then 75% is going to fall, let's see, 37.1, 47, 53. It's like 65. It's going to be 73. So 75% is going to fall in this one right here. All right, so that means our interquartile range is 7 minus 3, or 4. All right. Again, if our distribution had been symmetric, then we might have looked at the mean and the standard deviation. But because we're skewed right, we're better off looking at the median and then things like the range and the IQR because they are less susceptible to outliers. All right, so there's one problem. Making a histogram, being able to look at that histogram and kind of analyze the shape, center, and spread. And this is something that you could see on an open-ended question. All right, number 2. Below is some data on the relationship between the price of a certain manufacturer's computer monitors and the area of the screen. We would like to use these data to predict the price of monitors based on size. Sketch a scatter plot of this data. Be sure to label your axes with your variables. All right, so I have the data entered here onto my calculator. Again, I don't need like a super exact scatter plot. I'm looking for a sketch. So you are welcome to go to second y equals, turn your stat plot on. The scatter plot is the very first choice there. All right, my x is in L1, my y is in L2. And then if I go to zoom, go to graph, you're not really going to see anything. But if I go to zoom 9, that's zoom stat, that'll give me my scatter plot. So I can say, all right, here's my scatter plot. We've got a point here. We've got a point here. And then we've got 2 up here. And it does say to label your axes. So for us, this would be screen area. And this right here would be price. All right. But this is enough. I don't need like, the hash marks and saying, oh, this corresponds to this value. This corresponds to this value. I'm just looking for a shape that shows a sketch that shows me the general shape, right? Are we looking at a linear scatter plot here? Is this something where we're going to be able to use regression, or is regression not going to be an appropriate tool? All right, and this picture gives me that information without me knowing the exact, location and values of each of those points. All right, so if we continue, it says, use your calculator to find the equation of the least squares regression lines. Be sure to define any variables. So you either write the equation with x and y and then let me know what x and y are, or you write the equation with the actual variables that they're giving me. So I could write it like this. Predicted price, right? And now to get the actual equation, I go to stat, calc, linreg, and again, I can use 4 or 8. They're going to give me the same answer. It's just putting the slope in a different variable. L1, L2, hit calculate. All right, so this is saying predicted price equals 0.804 times screen size plus 88.4197, we'll say. All right, so that is one way you could write it, or you could write it as predicted y equals 0.804x plus 88.4197. But then you should just give me a little kind of note over here that, y is price and x is screen size. All right, but basically what this is showing us is as your screen size goes up, the price of the TV is going to also go up. All right, and by this scale, for each square inch that you add, it's going to go up by about, 80 cents or so. All right, now that might not seem like a lot, but 1 square inch isn't a lot. So most of the time you're going to go up by 100 square inches or 200 square inches, and then that is going to work out to be some real money. Okay, but that's what the equation is kind of saying. You give me the screen size, and I can give you a prediction of the price. This manufacturer also produces a monitor with a screen size of 950 square inches. Would it be reasonable to use this equation to predict the price of that television? Explain. So to do this, we have to look at our data set. And if you look at our data set, you're going to notice that 950 square inches is significantly larger than any of the TVs that we have any of the monitors that we have currently analyzed. They're not TVs, they're monitors. So should we use our equation to make this prediction? Right. The answer is no. 950 is outside of our data range. And then to throw a little vocab, using 950 would be an example of extrapolation, which often leads to poor results. Right? We don't know if our model or if our relationship holds for those values because we don't have any data on them. So trying to make a prediction in that range is called extrapolation, and that usually gives very unreliable and poor results. So we try to avoid it if we can. All right, a French accordion label, FARL, is planning a major investment in new talent. The amount of profit, X, in millions of dollars is uncertain, but a probabilistic estimate gives the following distribution in millions of dollars. Find and interpret the mean of X, show your work. So this is basically saying, what is the expected value of X? And the expected value of X is just the sum of the payoffs times the probabilities. So in this case, it would just be 1 times 0.02 plus 2 times 0.08 plus 4 times 0.2 plus 10 times 0.7. All right, and when we do that, 1 times 0.02 plus 2 times 0.08 plus 4 times 0.2 plus 10 times 0.7, it gives us a value of 7.98. So that would be our expected value of this situation, the expected profit. Find and interpret the standard deviation of x. So generally, this is what we're going to do on our calculator, and it's going to give us a chance to make sure that we got the right answer here. So if we go to Stat Edit, we're going to put in our payouts, 1, 2, 4, 10, 0.02, 0.08, 0.2, 0.7, and then we're going to go to Stat Calc, one variable stats. All right, so everything's in there. And then Stat Calc, one variable stats. We're going to go list L1, and then we're going to do frequency list L2. All right, so we're going to go Stat Calc, one variable stat, and then our list is L1, and our frequency list is L2. All right, once we do that, we'll hit calculate. Notice that our mean is 7.98, which is exactly what we found by hand, so that's good. And then our standard deviation, right? Notice there's no sample standard deviation because we're dealing with probabilities here. Our standard deviation is 3.14. So the standard deviation of x is 3.14. And as far as what this means, it is the average, and this is the definition we've been using all year, average distance from the mean. All right, so we have this mean of 7.98. Not every observation is going to be exactly 7.98. Some are going to be higher, some are going to be lower. On average, we're going to be 3.14 from this mean. All right, last part. FARL uses scouts to find its talents, and most pay a fee of $100,000 plus 10% of the profits X. So the firm actually retains 0.9x minus 0.1 from the investment. Use a linear transformation of your results in A and B to find the mean and standard deviation of Y. All right, so this goes into the rules that we learned about. Now, when you're talking about the mean, both addition, subtraction, and multiplication, division impact the mean. All right, so both of these change the mean. When we're talking about standard deviation, only multiplication and division change the standard deviation. So with this transformation here, this is multiplication. It's going to affect the mean and the standard deviation. This is subtraction. It's only going to affect the mean. So down here, we're going to be looking at 7.98, our original mean, times the 0.9 subtracted by the 0.1. All right. The reason it's 0.1 is this is $100,000. This is in millions. So $100,000 is 0.1 million, if you're wondering where that 0.1 is coming from. And then over here, the standard deviation is only impacted by multiplication and division. So this is just going to be 3.14 times 0.9. And we're going to leave out the subtracting of the 0.1. So this is going to give us a new value of 7.082. And this is going to give us a new value of 2.826. So this is our new mean. And this is our new standard deviation. All right. So again, these are all questions that you could see on the open-ended part of your final exam. So you want to make sure you know how to do these. And if you're having any questions or something didn't make sense, you want to make sure you reach out and get it cleared up before the test. All right. Have a great day.